Good morning. Webcam. Webcam is not working today. Fantastic. Okay, I guess today we are going camless. I thought I'd start today by heat waves coming in. Monday, Saturday, Sunday is supposed to be like 39 degrees. So two things. First, I'm going to talk a little bit about assignment 4 and just give some tips because last semester, 2 semesters ago when I gave this assignment, there was some confusion. So I thought I'd go over it in a lecture video just so that it's there in video form with some advice in case people encounter the same problems before they happen. And two, it is going to be like incredibly hot. It's supposed to be like 40 degrees on Saturday, Sunday, and Monday, which is absurd if you live here. If it's too hot and you literally cannot focus on work and you can't get your assignment in on Thursday, and that's a valid excuse for you, let me know. I can give you a 2-day extension. It's gonna delay you getting solutions for a bit, you personally, which might make it a little bit harder to study in time for the second test, which is a week after the assignment is due on Thursday. So the assignment's due on the 2nd. The second test is on the 9th. But if the heat is delaying you in terms of getting stuff done, just let me know because the assignment is worth 10%, the test is worth 12 and a half. So I mean the assignment is worth just as much as the test in the end. So um, whatever works best for you. Okay, so the assignment. Question 1 is just asking you to do 2 of the compositional trees. And the only thing about question 1 is that you have the ambiguous structures. So we did the ambiguous structure in the very last slide of the truth conditional meaning of sentences lecture. One was in the lecture, the other one was in the linked video, which is in the modules section from the previous semester. So please see both if you want to know how to do the trees. It's a pretty similar tree to the one in the last slide. There's a negation and there's a conjunction in there. I've italicized those. So treat even though as a single conjunction. It's just under conj. You'll have to figure out if this is an or an and in equivalence, but it is one of those. Don't copy the one from the lecture slides. Do this on your own for practice, obviously, but it's very similar. Everything that you need to practice is in this question. Okay. Question 2. I'll talk about question 2 because the notation is a little bit different. But the practice here is that there's 3 situations specifically. What we've been doing is we've been doing things in our truth functions for like general situations V. But in this case, we're doing like specific situations. We're talking about the truth in a situation V1, the truth in a situation V2, and the truth in a situation V3, or values in V1 and V2 and V3. So it's like 3 different universes that we're analyzing. Okay. And basically, we're describing what's in those universes. And we're doing them in slightly different ways. So in situation V1, we're specifying that one sentence is true and every other sentence is false. But sentences are truth values, and verb phrases are sets or relations. So to help you out with V1, when we say something like, Mark is awake, this is a full sentence. This is a truth value. But this is equivalent to saying that the value of is awake, the semantic value of is awake, is the set containing Mark. Because if Mark is awake is true, this means that Mark is in the set of people who are awake. So this is the verb phrase. And all the people who are awake in that set or in that universe is just Mark. So when this here says every other sentence is false, this means that there are no other people who are awake. And when we take a look at all of the other verbs, so for example, we have fears. Well, in this other universe, there's no other sentence that's true. So nobody fears anybody else in this situation. So fears is the empty set. And you could construct another sentence and you could say, Mark fears Miguel sorry, I should specify this is V1 specifically, and that would be false because every other sentence in situation V1 is false. So Mark fears Miguel is false because every other sentence is false in V1. So each of these situations is different. Okay, so I just wanted to clarify that. Because even though we've worked with this in the trees, maybe it wasn't obvious how this notation goes back and forth and why situation V3 is in sets and why situation V2 and V1 are in truth values. Another thing to watch out for is introduces. So introduces is a ditransitive verb. So it needs 3 arguments. So you'll have to figure out how introduces works in order to do one of the sets later. Okay, if you have looked at this and you have any questions, like, do you have any questions about this if you have looked at this that I could answer right now? If you are typing something, let me just scroll down a little bit. So I did try to give an example of how you can answer this. So there's like 8 different little questions you have to answer. And basically for each one, you say in each situation what the value is. So if you're just given a verb phrase, you answer with like a set. So this is an intransitive verb, is filthy rich. So you're answering with singletons, like individual people. If you were to be given, say, a transitive verb, so if you have something like fears, then you'd be looking to answer with pairs. But if you were to be given something like fears Michael, let's say you were given something like fears Michael. Remember, at this point, this is a VP. This has an object in it already. So at this point in your tree, if you were to draw a syntactic tree, you're just looking for subjects. You're just looking for those X values. So you're really just looking for a bunch of little singletons there. So you're not writing that answer in pairs, you're just writing that answer in singletons. So we're still taking the syntactic tree, the composition in mind. So fears, you'd be writing everything in sets of pairs, but fears Michael, you'd be writing in singletons. So just like you would in the compositional tree. While if you have sentences, you'd be giving truth values for each of the situations because sentences are truth values. So question 1 is about building the structure, and sentence 2 is sort of like, well, assume that you have this structure already built, and now you're given information about the world or information about specific situations. What are the facts? So 3, 4, 5, 6, 7, 8 parts. And for these cases, D, E, F, G, and H, I mean, you could just use truth tables if you wanted to. That's another strategy that you could use, is just put them into propositional logic, figure out the facts, and then just draw truth tables. It's a little bit more work to do it that way, but that's one way to do it. Okay, the understanding and extension ones. These are just these exercises, specifically 3, is more just about reading than it is. Uh, sorry, I shouldn't say it's more about reading than thinking, because that sounds sort of insulting in a way. But this is how the question was intended to be written, is more about reading practice, because all this is saying we had a propositional logic system that is ones and zeros, but we can actually make a logic system that is more than ones and zeros. We can use any value between 1 and 0. We could use 0.5s, 0.25s, 0.33s, 0.6712. It doesn't matter. And there's a way we can do this. So I've given you a system of converting, like, not alpha, alpha and beta, alpha or beta, into this system that can do any value. So your job is to read 1, 2, and 3, figure out how that works, and then sort of prove that this works. So when it says verify that the definitions work, basically you just have to plug them into these values. And I've given you sort of the English description of how this works. So if you're wondering, how do I show this work? It's just plug it in. It seems like you're not really doing much, and you're not really doing that much. So if you're trying to show your work and you're thinking, well, how do I show more work? You just plug them in. D, P arrow Q. I didn't give you a definition for P arrow Q, so you might have to look back at the slides for the conditional to figure out how you can redefine the conditional in terms of or. So a hint here is a hint. You can redefine the conditional in terms of or. So you can check the conditional slide, and you might have to check the logic law slide. You can do either of those, but that's a helpful hint there. And then for E, you can just use these tables to fill out the rest of the chart. F is more of a thinking question. So this is where you'll have to use your linguistic brain to think of what other values, like if you had a 0.5 or a 0.25 or a 0.9, why might you use those? When might you use those? Okay. Question 4, the problem with exclusive or. A little bit more insight as to why we don't use exclusive or when we translate. I won't talk too much about this. You'll figure it out on your own. And then question 5. I won't talk too much about question 5 either. All I'll say about this is because I've seen problems with this in the past too. I've tried to, I think it's mainly, reading the instructions, but I'll just emphasize this. Draw the syntactic tree using the rules. So draw the syntactic tree using these rules, and then answer the questions using the syntactic tree. It's very important that you look at the syntactic tree using these rules, otherwise the question might get complicated. So remember when I said in class that the semantic rules that we use are based on the syntactic tree. When you apply a rule at a node, you have to build the meaning based on its daughters only, based on its children only. That's an important concept that you have to employ in this problem. And you can use the VP to VTN rule as an inspiration. So you'll have to look at you'll have to figure out how to do ditransitives, but use that VP to VTN rule as an inspiration for your ditransitives. So those are some hints for this assignment. This question number 5 is probably more challenging than the other questions you've had so far in the course. And on the 5th assignment, there will be questions similar to this that are much more challenging than anything else that you've seen in the course. And I'm aware it's a lot more challenging because, you're creating semantic rules. You're looking at tree structures, you're incorporating linguistics and mathematics. It is very mentally taxing and very difficult to do these. So I am aware these are tough, but what's important is that you try. So you get points for attempting these, even if you're wrong. So please just give it your best attempt. You'll get partial points for any attempt whatsoever. That's all I'm asking you to do in this course with these tough rules is give it an attempt. If you get it right, that's perfect. You get full points. If everybody gets it wrong, then, we scale things up. But if you can get it right, that's perfect. That's fantastic. Okay. Are there any questions about assignment 4 before we start the lecture on predicate logic?
Is the mark for the assignment 3 gonna be released soon?
Yeah, I'm gonna work on that right after class. I only have a few left to go. I've been a little bit slow with it this week. Just other things, and also my allergies have been absolutely destroying me. But I will get that done hopefully within the next 2 hours after class is over. Okay. So, predicate logic. We're jumping back into logic so quickly, and it's such a shame. But with our syntax, like all we could do with our trees was it is not the case that Jim likes Carol and Jim is happy. Our sentences were very boring, but we couldn't do common nouns because common nouns are sets. And we don't know how to deal with a set being an element of another set with our syntax. Because if we say dogs are happy, we have to say that the set of dogs is an element of the set of things that are happy. And this doesn't really make sense. Um, we need that to be like a subset relation. And also, dogs are happy. Dogs isn't really an element. Is it all dogs? Is it some dogs? It's really a quantified statement or a generic statement. It's not just a single thing. So we need a quantifier of some sort. And propositional logic doesn't let us do quantifiers. So if we want to make our syntax more interesting, we need a stronger logical foundation. We need a more powerful system to build off of. We need a concept of determiners. We need something that can describe words like the and every and all and and some would be nice too. In fact, if we had a system that could do few or many or most, well, that would be fantastic too, because we could do even more interesting sentences. If we could get words like happy, adjectives, wouldn't that be nice? Or PPs, like at the hotel. What if we could get CPs in there, like restrictive relative clauses, like the child who slept? Well, that would be really interesting too. In fact, really with predicate logic and our trees, we could do all of this stuff. It would just take a lot of innovation. In fact, with F1, we could kind of do this. It wouldn't be very nice, but we could do it. So, uh, in lecture, we're going to focus on this. We're going to focus on implementing these things. And then on your 6th assignment, you're going to see what some of the problems are with these words. And then on your 5th and 6th assignment, you're going to look at how you can do these sorts of things in trees. And these will be guided. So I'll give you some hints as to how these can work and how these rules can be implemented, and then you'll work on them on your own. So by the end of the course, our syntactic trees and our semantic trees are going to be a lot more interesting. And actually, these words really are a lot more complicated to implement than things like happy and at the hotel and who slept. But of course, whatever's taught is going to seem a lot easier than things you have to figure out on your own. So that's just the nature of it, but it doesn't make it any less intimidating regardless. So let's talk about why we need predicate logic in the first place and the advantages of it. and especially what it is in the first place. And here's the main problem that linguists have with propositional logic, and really philosophers too, in terms of argument's sake. Imagine we have these two sentences, Beethoven naps and Mozart naps. In propositional logic, we have to have two complete propositions, B and M. But in linguistics and even in philosophy, we're aware that, we have the same predicate in each sentence. We have naps. They're both doing the same thing. It's just that the subjects are different, Beethoven and Mozart, but they're both doing the same action. So there is some similarity between both of these propositions. So what predicate logic allows us to do is use predicates as a base and take our nouns, our subjects and objects, and make them arguments. So, sort of like functions, well, really predicates are functions. In fact, when we first learned in the course, we learned about these things called characteristic functions or predicates. They're these functions that assign things to be true or false. That's what predicate logic is about. So now what we can do is instead of saying Beethoven naps is B and Mozart naps is M, we can use the predicate as a function itself. So we can say naps is a predicate. We can define it loosely. We can say this is nx, or we can say this is naps x. You can do either. I like to write out the whole word because that way I just know what everything means. And that way I can just read it and understand it. So I can say this is naps x. So this tells me that the verb is naps, or the predicate is naps, and it's intransitive. So it just takes one argument. So there's going to be some noun that goes in there, some person's name. And if I want to say Beethoven naps, then I put Beethoven's name in there, and that sentence is now Beethoven naps. If Mozart naps, I could put Mozart's name in there, and then it becomes Mozart's naps. And if I want to put the full name in, I'll write the full name so that way it's easy to read. But I might write it shorthand and I might say like NB or NM. It's up to you, whichever one is easier. The difference between writing the full version or the short version is that if you do the short version, you have to define keys so that way people know what you're talking about. If you just write NX, then people don't know what N means, they don't know what M means, they don't know what B means. But if you write Naps Beethoven, then it's very clear what everything means. So when going from propositional to predicate logic, we get something that's much more linguistic in nature, something that matches our syntax a lot more closely. So when you think about just syntax in general, predicate logic matches verbs and complements. So your subjects and objects and indirect objects in sentences. Predicate logic, now I'll write this very clearly here. Predicate logic does not handle adjuncts. So we do not include any sort of adjunct stuff like in the house or on the stove, any sort of that optional information. We do not do that in predicate logic. We just do subject, object, indirect object, that kind of stuff. If we do want to put adjuncts in there, normally what we do is we include them as part of the verb or part of the predicate itself. So I need to make this smaller. I'll just write, if we do, it's part of the predicate. So we could say the predicate is like naps in-house, and then we put Beethoven. So naps in-house. Beethoven. And we can talk about why a little bit later, but I don't want to muddy up the conversation with that right now. Okay, so this is a huge advantage with predicate logic. The other thing it lets us do is it lets us use quantifiers and pronouns. So we can now use words like every, and we can use words like some, and we can account for pronouns like she, he, they, it, and so on. That's it, not lit. So I have some translations here. We're going to talk about translations when they come, so they're just here for an example. Let's not look at them right now. But we can now say things like every cat is sleeping, some girl likes David, and she likes David. So I'm just going to show you the operators here. So we can put things outside of brackets. So this is an upside down A. This is what's called the universal operator. So this is like for all X, for everything in our universe that is X. So this would say for all X that are cats, they are sleeping. For this one is a backwards E. This is called the existential. Existential. This is the word for some. So this would be like for some X that is a girl. So for some X such that X is a girl, we could say X likes David in this case. And then there are some cases where there is no operator at all, and you would just have a variable on its own. So in this case, there's nothing, we call this binding a variable. And when you have a variable on its own, what you get is a pronoun. And why this happens is because variables just mean that, a variable is something that is variable. It's dependent on context. So pronouns are like that in real life. What she or he or they or it refers to in the real world is variable it's dependent on the context. If I say she in real life, it depends on where I am, it depends on who I'm talking about, it depends on what the other speaker knows. It depends on what the conversation's about. And it's sort of the same thing here, except with predicate logic. It's not really obvious what X is. X just maps to some person. So the specific pronoun we choose, it doesn't really matter. It could be she or he or it or they. It's all just an arbitrary pronoun. So I picked she for this translation for she likes David, but it could be he likes David or it likes David or they like David. It doesn't really matter. But in the description, I can be more specific. So in this one, I say X likes David, where X maps to some individual whose conceptual gender is female. Some of you might be wondering what the term conceptual gender means. Conceptual gender is a term coined by Ackerman 2020. This is, or maybe this was 2019, I can't remember. Ackerman is in the singular they research field. So I did my thesis on singular they too. This is a new term. So this is the gender that is assumed by others when they perceive you. So this is the gender that people, so when someone sees you, they assume a gender, and this is the gender that people pick their pronouns when they initially say a sentence. So there's different types of gender. These are the terms that haven't been used in syntax yet, but they're slowly coming into play. The terms in syntax for gender are constantly changing. Ackermann is trying to establish a bunch of different terms. So this is the term that is trying to become used in semantics at this point. So I'm trying to use it as well. So maybe I'll just type this in. I need to make this text smaller. The gender that is assumed, sorry. That's a better word, the gender that is presupposed by the speaker.
I have a question.
Yes.
So for A, we're using a conditional, but why for B are we using an and?
We'll talk about that when we do translation. So we're going to talk specifically about universal and existential translations on Tuesday. So we won't worry about that today. Today, we're just going to focus on the syntax and the scope if we have time. But we will have an exercise as well on Tuesday that shows specifically why we cannot use the conjunction for the universal and specifically why we cannot use the conditional for the existential. So not only will we explain it, but you'll be able to work and show why you can't use the other one. Okay. Here's a little technique, and we're going to come back to this technique as well. But with every sentence in quantificational logic or predicate logic, you can divide a sentence into these interpretive components. You can take quantified noun phrases outside of what's called the nucleus. So you have quantified expressions. So quantified expressions are any common noun with some quantifier with them. And sometimes the quantifier is like invisible. So it's like an implied quantifier. So here we have like a determiner every, and we have a noun. So this is a quantified expression. And then you have this nucleus that contains the content. So this is like your verb with like the frame. So what we can do, and let me just type this out here. So every bird is flying. What we could do is we can take any quantified expression out of our sentence, and we can move it to the front, and we can give it an index. So we can say every bird, and we can say X, and we can replace those quantified expressions with a pronoun. So every bird X, it X is flying. So what we're left with is a quantified expression. We can call this a quantified phrase if we want, but that's really not good because in syntax, that's something else. So don't tell anyone I did that, they'll kill me. We'll call it a QE, and then we'll call it the remaining stuff a nucleus. So it is flying. So it is flying gives us the same content, and it's indexed with every bird. So we know what's flying. And this can help us for translation later. So at that point, we can then split the quantifier, so every X, bird X, with the remainder of the sentence. So we could keep it is flying, or we could say X is flying. And then we could do a direct translation from there. So we can see this process coming to light a little bit later when we talk about translation. But what's nice about predicate logic is just like propositional logic, we're going to have a direct way to translate our sentences, a nice formulaic way of translating sentences. So this is probably something that you were never taught in a philosophy course or in a discrete math course for translating sentences. But this is also a way that we can get scope ambiguous sentences translated. Because when you have two quantified expressions, it's just, well, which one do you bring to the front first? Well, it's just, that's how scope ambiguity works. Which one do you bring to the front first? You have two choices. Depending on which choice you make is how you get the scope ambiguity. So again, we'll talk about translation on Tuesday, but you have quantified expressions, you have a nucleus, you can split the quantified expression up from the nucleus, and how you bring out the quantified expressions is how you get ambiguity when you have more than one quantified expression. And we'll see that in action later, so just a preview. Okay, so here's our syntax for predicate logic. And a lot of it is very similar to propositional logic. There's just a few more things. So first of all, and I'll just type this out. We have everything from propositional logic. That's the base. Everything you remember from propositional logic, we still have. So in predicate logic, P and Q is still completely valid. That is a well-formed formula. We don't see it that often, but it's okay. Okay. What we do have, though, is a lot of new stuff. So first of all, we have these things called terms. And terms are things that go inside the predicate. So these are essentially our nouns and pronouns. Well, and specifically variables. So we have constants. So constants are our elements. So you can use lowercase letters, A, B, C, D, and so on. Typically, we use the beginning or the middle of the alphabet for these, or you can just use full names. So these correspond to actual people in the world. So Kate, John, Mary, and so on. Variables we use at the end of the alphabet. So usually X, Y, Z, sometimes W, sometimes V. So these correspond to pronouns like he, she, it, or these are variables that will be bound. So, or for being bound by the universal, or by the existential or the universal. So I'll just put some or all. So we'll talk about what being bound means in a bit. Predicates. So these are our verbs. So these are our verbs. These could also be adjectives or prepositions. They might even be nouns in some cases. So really, when I say nouns up here, I should say proper nouns. Verbs, adjectives, prepositions, or predicates, the predicates are verbs, adjectives, prepositions, nouns, anything that's a set. So we have things that are like one place predicates. So our intransitive verbs like sleeps is happy, eats. You have two place predicates like likes, hates, loves, washes. Three place predicates like introduces, gives, sends. So we've seen these a few different times. We saw these and well, we worked with these last week on Tuesday. We worked with those in relations, and we'll work with these again in predicate logic. So specifically too, we might also have something like dog X. So this corresponds to like X is a dog. So you might have something like dog Fido, meaning that Fido is a dog. So that could be another example of a one-place predicate. We have the identity operator. I don't use this too much, but I do use it occasionally. So this is like is. So you might see like T1 equals T2. This just means like T1 is T2. So you could say that like two people are the same thing or two things are the same thing through this one. We have all the connectives of propositional logic. These are the same. We have our two quantifiers, the universal and the existential, and we have brackets. So these are all the things that we have in predicate logic. So a lot of these, like the predicates you've seen before, the terms you've seen before and other things, it's just, getting used to what does it usually mean when you see an X? What does it usually mean when you see a B? And then, what does the upside down A mean and what does the backwards E mean? And the key word, of course, when you want to remember the mnemonics for these, it's all and exists. That's usually how you remember these, for all and exists. So if you write those two words down like that, that can usually help jog your memory. All and exists. And then, of course, synonyms of those. So all and unfortunately every also starts with an E, but just remember the upside down A is all in its paraphrases and the backwards E is exists in all of its paraphrases. Usually, um, the key words for both of those that you see the most are some in linguistics and every. So every is usually the universal word and the some is usually the existential word that you see the most often. Okay. Before we move on, are there any questions about the building blocks? Okay, so how do we make a well-formed formula? Well, okay, so here's how well-formed formulas work. So this is a little texty, I know, but I'll just illustrate these on the side. When you have a predicate, let's actually use something like rains. You can have just a predicate on its own. Rains, for example, any of the weather verbs like it rains or it snows, these are predicates that do not take any arguments. So you can have a zero place predicate. This is fine on its own, so it does not need a term. This is a well-formed formula. But you can also have something like sleeps X. This is well-formed. You can have a transitive verb. You can have a ditransitive verb. So basically, um, if you have some predicate and you have like x1, x2, x3, x4, you can have any amount of terms in there as long as it's a finite amount. And this will break up into all of its individual components. So x2, x3, all the way up until it gets to its final term. So as long as you have a predicate and any number of terms, that will form together into a well-formed formula. In linguistics, typically we just stick to 0, 1, 2, or 3 because there aren't very many languages that have more than ditransitive verbs. Typically, 3 terms is the most you get with ditransitive verbs. If you have 2 terms on their own, these can be constants. So you can have you can have variables. Let's not use T1 and T2. Let's say we have 2 variables. You could have x equals y. You could have a variable and a constant, x equals a, or you could have 2 constants, a equals b, and these would be okay. You could also have a equals x. So you could have any 2 terms and you could say they equal each other, and those are also well-formed. If you have any 2 well-formed formulas, you can do any of the operators on them. So we could say something like sleeps x, if and only if, likes predicate X, and that would also be well-formed. So just like before, this would be of the form alpha, if and only if, beta. Just instead of P's and Q's, we're using things that are a little bit more complicated. Finally, now that we have the universal and the existential quantifiers, we can take any well-formed formula. So let's say we have something like sleeps X. We can put some brackets around it. I like to use square brackets just so I know where the universals and quantifiers are going, but it doesn't matter what type of bracket I use. I just use square brackets for my own reading ease. And then we can put a quantifier around it with a variable. It needs to have a variable. It can be whatever variable you want, but it has to have a variable. And then that is well-formed. So exists the next reigns. That would also be okay. But those have to be bound, those have to go around a well-formed formula. You cannot just have exists in X on its own, or you cannot just have the existential on its own. And you cannot just have something like exists and then reigns Y. Like, you cannot have that. It needs to have a variable with it. So this is how we do well-formed formulas in predicate logic. That's my next slide. Okay. Does exists in X, and if alpha was reigns Y, is that unbound? Yeah, that would be unbound. We'll talk about binding in another slide coming up. Like I'll introduce binding very specifically. But that would be unbound. Okay, so just to show you how this works with a very simple structure, we can do this with trees as well. So if we have there exists an X for MJX, we don't know what MJ and X mean in this case. This is just a random set of predicates and terms and existential here. We see that the predicate M, J, and X join together to make MJX. Because this is well formed, we can attach the existential quantifier to it, and then we get there exists an X such that MJX to it. So this is now a well-formed formula. And how to read this, we could say there exists an X such that MJX, and then whatever MJX means. So we could say there exists an X such that J M's X. That might be the English form for it. So typically, reading left to right, if this were English, the first thing would be the subject, and the second thing would be the object. So a paraphrase would be J M's X in English. Or there's some X that such that J M's X. That could be another way it's paraphrased. So we don't quite have enough time to do the exercise, so we'll start with that on Tuesday, but this was just a nice light intro to predicate logic with the syntax to help you get familiar with it. So we can cover that or review it on Tuesday and start with an exercise. But yeah, that's all we have for today. If you have any questions, you can stick around, but that's all I wanted to cover today.
Is the SFU vault working now?
Yeah, SFU Vault is working at this point. They updated the client, so I had to download something new and resync everything. The 6.2 lecture was lost from my vault, so I don't have the file anymore. It's on YouTube, but I don't have the file. So yeah, it's not gonna be on Vault, but it is on YouTube. everything else from here on out should be on vault again.
Thank you.
Yeah. So I will stop the recording.